Historically, interacting with a large language model required a deliberate human trigger. You type a prompt, you wait for a response, and the moment you close the browser tab, the execution stops. LLMs are now being deployed as persistent, goal-oriented agents that run continuously in the background, independent of an open browser window or active user session. To understand how this functions in practice, we are going to deconstruct two specific autonomous architectures built entirely without traditional code. The first is a scheduled data pipeline, a system that scrapes the web, curates specific information, and delivers it on a daily schedule without human intervention. The second is a conversational data routing system connected to an auto-generated web front end designed to capture and process unstructured human requests. Natural language has become the configuration layer for system logic, execution scheduling, and error handling. We are watching the replacement of deterministic, rules-based automation with probabilistic, goal-oriented execution environments. Deploying these autonomous workflows requires a specific infrastructure. Rather than chaining together disparate third-party tools, the entire execution runs directly inside the Anthropic developer console. This diagram shows the three critical components of that architecture. At the center is the environment. This is a sandboxed workspace with highly restricted networking, where the agent is allowed to execute the tools you give it. Connected to that sandbox is the vault. Any external API credentials or access tokens required for the agent to communicate with outside applications are encrypted and securely stored here. Beside it sits the session log. Because the agent is operating autonomously, this immutable notebook tracks the granular details, logging every single tool call, logical deduction step, and system response as they happen. Operating in tandem, these three components ensure the agent has the necessary access to perform its task, while remaining walled off from any external systems or private data it shouldn't touch. This three-pillar setup provides the isolation and security necessary for LLMs to function as reliable background execution engines. The operational goal for our first architecture is straightforward. We need an agent to deliver a Slack digest every morning at 7 a.m. summarizing AI industry news from the previous day. This workflow tree illustrates how a single natural language prompt establishes the data pipeline. From one text block, the prompt directs the agent to pull raw data across 4 separate branching paths: general web search, Twitter, Reddit, and specific tech blogs. Embedded within that same text block is a strict temporal constraint. The instructions explicitly restrict the agent to retrieve only information published within the last 24 hours. Next is a state check instruction. Before drafting its digest, the agent is directed to read the existing Slack channel history. This prevents it from posting duplicate articles that were already covered the day before. Finally, the prompt forces the gathered data into a strict output schema. Every post must follow a precise format: a headline, a 2-sentence summary, a source link, and a timestamp. The agent takes these plain English parameters and translates them into sequential tool calls, operating securely inside its sandbox environment to query the web and format the results. You do not have to trust that the agent followed the sequence blindly. You can open the session log to read the step-by-step breakdown of its web searches and parsing logic. A single paragraph of natural language has successfully configured a complex multi-source data ingestion pipeline. Building this level of automated scraping and formatting previously required dedicated middleware engineers. During the initial test run, the pipeline executes, but there is a logic failure. The agent successfully pulls news and formats it, but it ignores the temporal constraint, bringing in articles from several days ago. In a traditional automation platform, correcting a date parsing error requires opening a visual workflow editor, locating a date filter node, and manually configuring a new relative time range. Here, that process is replaced by conversational logic. You simply type a single sentence of correction into the prompt interface. Check today's date first, then strictly filter to news from the last 24 hours only. This feedback triggers an internal mechanism. The agent digests the conversational instruction and autonomously rewrites its own system prompt, baking the new chronological rule directly into its core logic. On the subsequent test run, the output is clean. The conversational debug successfully locked in the operational constraint. The final element is scheduling. Instead of setting up external cron jobs, you type a simple prompt asking Claude to run this specific session every morning at 7 a.m. It executes exactly as requested, effectively establishing a persistent daily execution sequence without relying on any external server infrastructure. Debugging logic errors through dynamic prompt rewriting bypasses traditional visual logic nodes, changing how automated systems are maintained. The second architectural challenge moves from scheduled scraping to asynchronous data capture. We need an agent that fields inbound client requests 24 hours a day. The standard industry practice for capturing this data is a static, multi-field web form. The user either fills out the entire form or they abandon the interaction. This diagram breaks down the core operational logic of our alternative. The agent's goal is to extract 4 specific variables from unstructured conversation: name, phone, email, and need. Instead of dropping a form link, the agent maintains conversational state. It asks a question, extracts the relevant data point from the human's unstructured reply, and loops back to ask for the next missing variable, guiding the interaction step by step. Once all 4 parameters are fulfilled, the execution step triggers. The agent packages the extracted variables into a structured payload and routes it directly into a private Slack direct message. This secure routing happens seamlessly because the agent utilizes the API credentials we previously stored in the platform's encrypted vault. By maintaining conversational state, the system extracts highly structured data out of fluid, unpredictable human interactions. There is one immediate deployment limitation with this setup. Managed agents natively exist only within the developer console preview, which is inaccessible to regular clients. To bridge this backend agent to a public-facing audience, we need a web interface. This image shows the Claude Code CLI environment. The handoff process is simple. The developer takes the raw configuration code generated by the managed agent and feeds it directly into the Claude Code terminal. In response, Claude Code instantly generates the required HTML, CSS, and connection logic to stand up a clean, functional chat interface layout. This completely bypasses the manual construction of a user interface while perfectly preserving the secure backend logic routing the data to Slack. With a single prompt to a code generator, we have established a complete end-to-end pipeline, from a public-facing conversation to a private internal notification, with 0 manual coding. This diagram illustrates the architecture behind persistent, scheduled pipelines and state-maintaining conversational routers, the environment, the vault, and the session log. Operating together, these pillars allow developers to bypass the brittle logic gates of traditional integration platforms. They provide the exact transparency and security required to deploy autonomous, goal-oriented systems securely within strict enterprise environments. This structure shifts the role of the technical practitioner. The job is no longer writing rigid middleware code to connect disparate APIs. It is engineering precise, probabilistic system logic. System execution is no longer limited by a developer's knowledge of specific syntax, but by their capacity for clear architectural thinking. The bottleneck in deploying complex automated systems is no longer the code. It is the precision of your natural language system design.
A high-value client decides they want to work with your firm. The only problem is they are browsing your site at 2 a.m, long after your sales team has gone offline. Drop a static web contact form in front of them, and you guarantee a high abandonment rate. Users expect immediate engagement, and often move on the moment they realize they're just waiting for an email reply. The standard industry alternative is the rigid decision tree chatbot. These systems fail the moment a user provides input that falls outside of a pre-programmed linear path. To capture intent during off hours, we have to look past these legacy methods and analyze the architecture of a stateful, autonomous ingestion engine. Instead of simple prompt response generation, where an AI answers isolated questions and stops, goal-oriented logic drives the interaction towards specific, required variables. Moving from passive scripts to proactive data extraction pipelines allows for a lead capture process that doesn't rely on human presence. Most traditional language model deployments suffer from a fatal constraint. The memory and the process die the exact moment the user closes the browser tab. Anthropic's managed agents operate with a continuous runtime. The logic engine executes tasks independently, meaning it can process and deliver information whether a user is actively viewing a window or not. This diagram shows architectural decoupling. We detach heavy conversational logic from the front-end interface. By centralizing logic in the backend, the user-facing shell becomes disposable. Complex API routing remains securely on the server, while the surface interface is modified without touching the core logic.
This structural foundation allows us to build a persistent AI receptionist that functions 24/7 without requiring a live browser session. The Anthropic console is the central hub for configuring the agent's architecture, starting with the security layer. The environment module provides a private computing space to process logic. Isolating the agent in a sandboxed runtime prevents it from executing unauthorized API calls. Alongside it, the Vault module functions as the encrypted credential manager for the system. Sensitive data, like a Slack API token, is stored securely in the Vault rather than being hard-coded into the core prompt. Skipping these sandboxing steps introduces severe operational risks. Securing the execution environment and managing credentials is the mandatory prerequisite for autonomous enterprise tool calling. Programming a conversational agent with rigid, step-by-step scripts often leads to frustrated users who drop off when the bot cannot handle a nonlinear conversation. Instead, we use constraint-based prompting. We define a goal space consisting of 4 specific variables: name, email, phone, and need. The agent's singular directive is to extract data to fill these 4 nodes, regardless of the conversational path. The system calculates its next question based on which nodes remain empty. This allows for natural, single-turn extraction, rather than dumping a long, static form on the user at the start of the interaction. If a user asks about pricing first, the agent answers the query, then immediately returns to the missing phone field to complete the profile. This maps a fluid boundary for data extraction that rigid decision trees cannot match. Consider a scenario where a potential client sends a message saying, "I'm interested in working with you," late at night. Inside the Anthropic console, the Sessions tab acts as the system log, recording every step of this interaction. The agent reads the input, identifies the empty data nodes, and begins the conversational loop. It extracts the name, phone number, and email before finally asking exactly what the client needs. The moment the constraints are met, the agent initiates the external tool call. It structures the text into a payload, authenticating via the Vault token to push data into the Slack workspace. Successful tool calling transforms the language model from a passive answering machine into an active data delivery pipeline. To make this useful, we have to migrate the agent from the developer preview console into a public user-facing shell. Because of the decoupled architecture, the front-end code only needs to pass basic API parameters back to Anthropic. By feeding the managed agent's parameters into a code generation tool like Claude Code, the interface creation is automated. This process generates a deployable HTML and React foundation for the web chat in seconds. Using a disposable front-end allows user interfaces to be spun up or torn down in minutes, without risking the underlying logic. The lead data moves from the user interface through the API gateway into the Anthropic environment, where it is authenticated by the Vault and delivered as a Slack payload. This entire routing pipeline is executed autonomously, without human intervention. This architecture scales effectively beyond simple website leads. These stateful, goal-oriented systems can replace static data collection tools across HR, procurement, and daily enterprise operations. Adopting this structure ensures that high-value intent is captured at the moment of peak interest, rather than being lost to an empty inbox. Technical founders can use this to move away from stateless implementations that inherently leak data during session timeouts. Transitioning to goal-oriented execution allows companies to turn conversational input into structured operational work that runs continuously around the clock.
Thank you for watching my video. If you like this, please share and subscribe. Bye. We will meet in next video.